In this video, we'll learn how to predict the geometry or shape of a molecule or polyatomic ion using VSEPR theory. When we talk about the shape of a molecule, we're talking about the angles between the bonded atoms that surround the central atom. We use VSEPR theory because of the simplicity of the principles involved, as well as the accuracy of the predicted geometries. VSEPR theory is based on the concept that, since electrons are negatively charged and like charges repel, the groups of electrons that surround that central atom in a molecule, or polyatomic ion, will take on the shape that allows those electron groups to be as far away from each other as possible. A simple analogy can be made using balloons. Balloons also don't like to be scrunched together and will find a position that gives them as much space as possible. When there are two balloons tied together, they take on a shape where they're opposite each other. When there are three balloons tied together, they take on a triangle shape. Four balloons tied together take on a shape that looks like the bottom of a tripod. When there are five balloons tied together, we actually get a combination between the triangle shape that we saw before and the shape that we got when the balloons were opposite each other. We have the triangle in the middle with one balloon going up and one balloon going down. When we have six balloons, they take on this shape that looks a lot like a jack that you would remember from the childhood game. Applying this same idea to the geometry of molecules, where the electron groups take on the shape that gets them as far away from each other as possible, we get these same geometries. Also, there's a specific way to designate the geometries in VSEPR theory. We use the letter A to indicate the central atom, and X is used to represent atoms bonded to the central atom. So when two atoms are bonded to the central atom, we have a VSEPR designation of AX2, and the shape that we get is called linear. When we have three atoms bonded to that central atom, the VSEPR designation is AX3. That gives us that triangle we were talking about before. See that we have 120 degrees between the bonds in this particular geometry, which is much less than the 180 we had in the linear geometry. Because this triangle is all in one plane, the name of this shape is trigonal planar. When we have four atoms bonded to the central atom, the VSEPR designation is AX4, and the shape that we get that looked like that tripod is called tetrahedral. That's the name of the shape because if you were to put faces on the sides of this shape in the molecule, you would get a three-dimensional shape that has four sides to it. That's called a tetrahedron. In the shape that we get where we have five atoms bonded to the central atom, the VSEPR designation would be AX5. And in this particular shape, notice that all of the positions are not identical like they were in the first three geometries that we discussed. These atoms here in the center, we call these the equatorial positions, and they are 120 degrees apart. The two atoms in the axial positions are 90 degrees from the plane that contains the equatorial atoms. Because this geometry looks like one pyramid on the top and a second pyramid on the bottom, the name is trigonal bipyramidal. And lastly, when we have six atoms surrounding the central atom, The VSEPR designation is AX6, and the name of the shape is octahedral. Again, when we place faces onto this shape, we get a shape with 8 faces, which is an octahedron. Let's take a closer look. We always begin with the Lewis structure. Yes, that means that in order to determine the correct geometry, we have to be confident that we have the correct Lewis structure. In this case, we're looking at the molecule methane, CH4, and here's the Lewis structure. From here, we can get the VSEPR designation, A for the central atom, and we have 4 bonded atoms, so the VSEPR designation is AX4. And then from there, it leads us to the molecular geometry, which in this case is tetrahedral. But what if there are non-bonding electrons in our Lewis structure for a molecule? In this case, we're looking at the ammonia molecule, NH3. Even though the shape of a molecule, or a polyatomic ion, doesn't include any lone pairs, remember the shape comes from the angles between the bonds. So even though the shape doesn't include the lone pairs, those lone pairs still require their own space. They still need to be as far away from the other electrons as possible. So their presence must be taken into account when determining the geometry. So in the Lewis structure for ammonia, we see that there are 3 bonded atoms. So our designation will be AX3, but we also have the non-bonding pair, and in the VSEPR designation we use the letter E for the non-bonding electrons. So here our VSEPR designation is now AX3E. When we're counting how many groups of electrons that we need to account for to give them as much space as possible, we include both the bonded atoms and the unshared pairs. So we're looking at the total of the number of bonded atoms X and the number of electron pairs E. For us here, that's 4, 3X and 1E, a total of 4 groups. So our electron groups are going to take that tetrahedral shape. However, when we look at the shape of the molecule, we don't see this one position in the tetrahedron because there's no atom there. That position is occupied by a lone pair of electrons. What remains in our geometry is the central atom and these 3 positions for that original tetrahedron. Because this gives us a triangle, but it's not a triangle in the plane. The central atom, the nitrogen, sits higher up. We refer to this as a trigonal pyramid. So the shape of the ammonia molecule and any molecule with the VSEPR designation AX3E is trigonal pyramidal. What about the water molecule? If you're looking at the Lewis structure for the water molecule, we see that oxygen, the central atom, has 2 bonded atoms to it, 2 hydrogens, and 2 lone pairs of electrons. So that means that our VSEPR designation is AX2E2. Again, that's a total of 4 electron groups, but that means that our electrons do have the tetrahedral shape, but 2 of those positions aren't seen in the geometry of the molecule because they're occupied by lone pairs. This leaves us a geometry for the water molecule that is bent. So we can see how from the Lewis structure we can get the VSEPR designation, and then taking into account the geometry for the electrons and subtracting positions for each of the lone pairs, we can determine the molecular geometry. Summarizing all of these possible geometries when we have four groups of electrons, if all four of those groups are bonding groups, we have an AX4 VSEPR designation and a tetrahedral molecule. If three of those groups are bonding, but one is a non-bonding pair, we have an AX3E VSEPR designation and a trigonal pyramidal shape. When we have two bonding atoms and two lone pairs, we have a VSEPR designation of AX2E2 and the molecule is bent. Let's look now at a different Lewis structure. Here we have the Lewis structure for the carbonate atom. So if we're looking at the Lewis structure, we see that we have a central atom and we have three bonded atoms. So our VSEPR designation is AX3. We have no electron pairs on the central atom, so we don't have any E in our VSEPR designation. Also notice that it doesn't matter whether the bond is a double bond or a single bond. All we need to take into account for is the number of bonded atoms. As we'll see later, this is because the region of space that has a single bond is the same as the region of space that has a double or even a triple bond. So in this case, our VSEPR designation is AX3, so we know that that gives us a trigonal planar geometry. Looking at the Lewis structure for the nitride ion, we see that there is a central atom, A. We see that there are two bonded atoms, that's X2, and we see that there's one lone pair. So the VSEPR designation is AX2E. The 2 plus the 1 for the atoms and the lone pair gives us a total of 3 positions for electrons. That gives us the trigonal planar geometry. But again, in this case, one of those positions is not seen because there's no atom there. It is a lone pair. It needs to have its space and it occupies that position, but it does not show in the molecular geometry. So in this case, the nitride ion or anything with the VSEPR designation AX2E would be bent. Let's look at the carbon dioxide molecule. We can see from the Lewis structure that there's a central atom and there are two bonded atoms, but there are no lone pairs of electrons. This gives us a VSEPR designation of AX2 and the molecular geometry is linear. Now let's consider what happens when we have 5 groups of electrons that surround the central atom. In the VSEPR designation AX5, all 5 of those groups of electrons are bonding electrons. So the electron geometry is trigonal bipyramidal and also the molecular geometry is trigonal bipyramidal. Let's look now at what happens with those 5 groups of electrons when 4 of them are bonding, but one of them is a lone pair. We still have 5 groups of electrons that are going to take those positions in the trigonal bipyramid. However, one of those positions won't be seen in the molecular geometry. It's important to remember that with this geometry, there are 2 different types of positions. We have the equatorial positions that are in the triangle positions, and then we have the axial positions, one above and one below. Sorry about my PowerPoint there. One axial position above and one below. So it's important to remember that when a lone pair occupies one of those 5 positions, it will always be an equatorial position. So when that lone pair occupies this equatorial position, what's left if you were to turn it on its side, would kind of look like that playground equipment that we saw before when we were younger. And this geometry is called a seesaw. What if my VSEPR designation is AX3E2? I still have 5 groups of electrons to account for, but this time only 3 of them are bonding and 2 are lone pairs, so we need to remove a position, another position that's an equatorial position, and what we're left with is something that looks like a T, and we call it T-shaped. And finally, when we have 5 groups of electrons and 3 of them are electron pairs, we'll correct our VSEPR designation here. This would be A for the central atom, 2 for the X's, the bonded atoms, and 3 for the E's, the electron pairs. That means we remove the third position, the third equatorial position. We're left with only the axial positions, and the geometry is linear. And finally, looking at examples where we have 6 groups of electrons that surround the central atom. If all of them are bonding, we have an VSEPR designation of AX6, and we have an octahedral shape. However, when we have a VSEPR designation of AX5E and one of those positions is occupied by a lone pair, what we're left with looks like a square pyramid. So the shape of this molecule would be square pyramidal. If we have 2 lone pairs and only 4 bonding atoms, we have a VSEPR designation of AX4E2. We should remember that the positions that the electron pairs occupy are always opposite each other, and the shape that the molecule takes is square planar. And that's how we determine the geometries of molecules and polyatomic ions using VSEPR theory.